Hello, this is Mr. Waters with part B of our projectile motion examples here, and this one is going to be a little more complicated. On this one, as you can see, Carla is on the moon instead of being on the Earth, and she's going to hit a golf ball from the top of a 300-meter high cliff with an initial speed of 40 meters per second and an initial angle of 40 degrees. Okay, now the questions are going to be the same. Find the parametric equations for the motion. How long is the ball in the air? Since part of the ball has horizontal motion, we can determine there's going to be a horizontal distance that the ball travels, so we'll figure that. And then how long does it take for the ball from when she hits it for the ball to get to its max height, and what's the height? Okay, now you can see that that the questions are the same. It's just sort of the details of the situation are a little bit different. Okay, well, we're still going to use the same parametric equation formulas because it's still projectile motion. Doesn't matter that it's on the moon or she's hitting it from the top of a cliff. Okay, it's just that some of the initial conditions are a little bit different. Okay, so first off, we need to know the initial velocity. Well, the initial velocity is 40 meters per second. You notice here we're using metric units. And we have the initial angle there is 40 degrees. Okay? Now, we're given that the initial height, rather than 0, is 300 feet, because here's the cliff, right? There's the lunar surface at the bottom. Here's Carla here, and she's going to hit the ball. It's going to travel out, plop down here somewhere. Okay, and so what do we? So this is 300, right? Meters. And how long is the ball in the air? And then how far does it travel is going to be that distance there. Anyway, so we'll put that back in actually when we get to that part. Okay, so what else? Oh yeah, the G. Now that's the gravitational acceleration. Now the moon has a mass of 1/6 of the Earth in metric units, so that means that the gravity is 1/6, the gravitational acceleration. So in metric units, the Earth's gravitational acceleration is 9.8 meters per second squared. For the moon, it'll be 1/6 of that. So we divide, and according to my calculadora, this comes out to about 1.6 meters per second squared on the moon. So that's going to be gravity for the moon, gravitational acceleration. Okay, now, so over here to part A. Let's go ahead and figure out what these equations are going to be. Well, A, the horizontal motion parametric equation is going to be x. V naught is 40 meters per second times cosine 40 degrees, whatever that is, times t. B, the y, the vertical parametric equation is going to be negative 1/2 times 1.6, the lunar gravity, times t squared, plus initial speed of 40 times sine 40 degrees, all this times t, plus 300. Now you can see we're going to get out of this they're parametric equations, but they're going to be rather more complicated than the ones we had in the previous example. So again, my calculator is going to help us out here, and it's going to tell us that the cosine of 40 degrees, as it happens, is 0.766, and the sine of 40 degrees is 0.643. Now we just plug all that information into the equation here. So our x parametric is going to be 40 times 0.766 times t. So it just so happens that when you multiply those out, you get about 30.64, so that's 30.64 t, okay? And then let me scroll down a little bit here so we got more room. Okay, the y is equal to negative 1/2 times 1.6 is about negative 0.8, or 0.8 t squared, plus 40. Okay, that sine of 40 plus 40 times, and then the sine of 40 was 0.643, so that's going to be 0.643 times t plus 300, that's the initial height. 40 times 0.643, as it turns out, is 25.72, rounded off. So here's the answer to A, our two parametric equations. X is equal to 30.64 t, and y is equal to negative 0.8 t squared plus 25.72 t plus 300. And so there they are. There's the answer to A, one of the parametric equations. Now B, going back up here, B asked us, how long is the ball in the air? Well, just like the earlier one, the time that the ball is in the air is the time between t equals 0 when it hits here, and t equals whatever the time is down here. Well, you see the ending time, the initial is at 300, the height, but the ending time is at y, the height is equal to 0. So what we do is we still take our vertical parametric equation and set for B, we're going to set y equal to 0. Now, of course, it's still a quadratic equation, but it's got those bizarre coefficients. We're not going to factor it or complete the square. We're going to use the quadratic formula. Plunk the numbers in. That's x is equal to opposite b, which is, so it's going to be negative 25.72 plus or minus the square root of b squared, which is 25.72 squared, minus 4 times a, which is negative 0.8, times c, which is 300, all over 2 times negative 0.8. Okay, now, of course, that's just calculator business there, which is how I did it. Okay, scrolling down here. Okay, so that's going to be, after I crunch the numbers for a while, that works out to be x, which you understand the x term in our quadratic equation here. The x term is the t, so what we're really solving for here when I say x is really the t. Okay, going back up here, let's get rid of this. Okay, that's really got to be the t, doesn't it? So let's put that in. This boils down to negative 25.72 plus or minus, after we simplify everything, 40 inside the radical, you understand. After I do the b squared minus 4ac, 40.26 over negative 1.6 after we multiply the 0.8 by 2. Anyway, so that works out to be negative 25 plus the 40, negative 25 minus the 40 divided by negative 1.6, and again, heating up the calculator gives us t is equal to 41.23 seconds, or negative 9.09 seconds. Now, the reason why we get a negative time there, you understand, is that mathematically, if we look at our curve, do this part in red, this little guy extends back into the negative distance. So this is technically, mathematically, this is the other spot where the graph is equal to 0, but where the y is equal to 0, but that's going to be negative 9.09 seconds in time back. So we want this one out here, which is the 41.23 seconds. Well, 41 seconds in the air with a golf ball. That's a long time in the air. Okay, and that's because the ball is so light and because the moon's gravity is so low. Okay, so that's how long it takes. That's how long the ball is going to be in the air, 41 seconds, according to the initial conditions. Now, the second part of this was we're supposed to, now that we've got the time, we're supposed to figure out how far it goes. Okay, so this is going to be c down here, the horizontal distance. Well, the horizontal distance is given by the horizontal parametric equation. So x, the horizontal distance, the range, is 30.64 times 41.23. Okay, we multiply those two together, and that works out to be, since we're in meters here, 1,266.3 meters, 1,200 meters, almost 1,300 meters horizontally. That's 3,000, what is it, meters, about 3 feet. That's close to 1,200 yards. Okay, that's quite a drive. Also consider the fact that she's starting off a 300-foot high cliff. Okay, so that's, you understand, 1,266 meters measured from the bottom of the cliff, you see, like that. So that's 1,266. Okay, now, D, the last part was we're supposed to be solving for how long it takes for the ball to reach its maximum height, which is right here at the vertex of the parabola, right, which is halfway between there and there, okay, and how high it is, what the vertical height is. Okay, so we're going to find, as you know, the vertex of that. Let me scroll up a little bit here further so we can see that picture better. The vertex is h comma k, and you'll recall we had that little formula, h equal to opposite b over 2a, and then to use the to find the vertex. So we're going to scroll back down. So h, which is that, which again is the, in our parametric is really t, that's the time. So let's make sure we know here that that's the time, because that's the input, the x variable for that parametric function. So t is opposite b over 2a, which is negative 25.72 over 2 times negative 0.8, which again, calculator, using the numbers on the calculator, is 16.075 seconds, or about 16.1 seconds. So it takes about 16 seconds. It's 1 1,000, 2 1,000, 3 1,000, 4 1,000, 5 1,000, 6 1,000, 7 1,000, 8 1,000, 9 1,000, 10 1,000, 11 1,000, 12 1,000, 13 1,000, 14 1,000, 15 1,000, 16 1,000. Now it's at its maximum height. And we'd keep counting to 41 before the ball hits the ground out there onto the lunar surface. So now the maximum, okay, so that's the time it takes to reach its maximum height. Now to get the vertical height, okay, obviously we want back in the parametric equation, we want to know the y, the height that's associated with that time of t. So it's going to be y is equal to negative 0.8, 16.1 seconds squared, plus 25.72 times 16.1 seconds, plus 300. More calculator crunching, And according to my calculator, hopefully I did this right, 506.73 meters. And that's, you understand, including the 300 that we started at. Okay, so that's going back up here. That's from here up. That is 506 meters. Anyway, so that's all we need from that problem. And thanks for listening. So there is, let's say, make sure we've got that. That's the answer to D there. That's the maximum height. And so thanks for listening. And that's all for tonight.